Hi, I'm Matt, and my project is Noisy Gradient Descent with Minibatching. My goal for this project was to implement noisy gradient descent with Minibatching. Additionally, I wanted to try my implementation with Renyi differential privacy and zero concentrated differential privacy. Noisy gradient descent is an optimization algorithm that finds a local minima. It is used to minimize a cost function, but it has a couple of big downsides. The first being that it's very computationally expensive. When computing a gradient, it uses the whole dataset every iteration. Another downside is the privacy cost, which is k times epsilon, k times delta differential privacy. The reason I wanted to use mini-batching is because it fixes the drawbacks of noisy gradient descent. Mini-batching helps improve computational efficiency, and it decreases the privacy cost because it allows you to calculate the gradient using a small chunk of the dataset in every iteration, as opposed to calculating the gradient using the whole dataset in every iteration. Doing this helps you significantly reduce runtime, and it also allows you to use parallel composition. The reason I could use parallel composition is because parallel composition states that you can break a dataset into multiple disjoint chunks and use a differential privacy mechanism on each chunk. But since an individual can be in no more than one chunk, a differential privacy mechanism can only be used on an individual one time. This leads to a privacy cost of epsilon. In order to implement mini-batching, I had to make several additions to the original noisy gradient descent code. To start, I shuffled the training dataset at the beginning of the algorithm. And then I used a for loop to create the batches of data. In my for loop, I started at 0, I went to the length of the training dataset, and then I used a step size of the length of the dataset divided by the number of iterations that would be performed. Next, I used a for loop to go through every iteration. In the for loop, I computed the gradients using the ith batch of data, as opposed to the whole training dataset. After that, I clipped the gradients and took the mean of the clipped gradients. Once I had the mean of the clipped gradients, I used the mean to compute the noisy gradient. When computing the noisy gradient, you had to decide between 3 functions depending on what kind of differential privacy you were using. After that, you set theta equal to theta minus the noisy gradient. And once the program has run through all the iterations, you return your theta value. Once I had implemented noisy gradient descent with mini-batching, I tested the accuracy of all 3 different kinds of differential privacy. In order to test the accuracy, I ran each algorithm 10 times and then took the mean of their accuracy. For the Gaussian mechanism, the accuracy actually increased by 0.002 when using mini-batching. For Renyi differential privacy, it decreased 0.003, and for zero concentrated differential privacy, it decreased 0.002. Additionally, mini-batching also reduced the privacy cost. Before mini-batching, k times epsilon, k times delta differential privacy was the total cost. After mini-batching, epsilon delta differential privacy was the total cost by parallel composition.